I'm going to be talking about securing physically unclonable functions, and it's kind of a redundant thing in there, or maybe a contradiction, that if physically unclonable functions are already supposed to be secure, so what is there to secure about them? This work has been sponsored by primarily by Intel and also NSF. Intel has been putting in physically unclonable functions onto their chips, but just not the type that we are investigating here, so that's what they were interested in. So I'll give a little bit of introduction, which will be pretty broad, and then we'll get into 3 specific topics. The first one is how to ensure uniqueness. The second one is how to make these PUFs more secure. And the third one is improving actual circuit level implementation of these PUFs. So let me start with the introduction. And as I said, the introduction is going to be fairly broad and general. So this you probably already know. You've seen slides like that from Christoph many times, that we have a large number of digital devices that surround us, and not only in our personal lives, but also in industrial sectors, which today we call industrial Internet of Things. Then we have personal Internet of Things. Then we have medical Internet of Things. So there are many different domains where there's a proliferation of these devices. By some estimate from IHS Markit, which is a market study organization based out of London, they estimate that today there are 17.6 billion connected devices in 2016. And I don't know if any of you have seen that article in Spectrum about the projection of how these things are going to grow. Of course, there are very rosy projections that we'll probably have 100 billion devices by now, but in reality, we probably will have something like 50 billion devices in another 5 years. Most of these devices, they operate in an unverified environment where the adversaries have high degree of physical access to these devices. And the key question that everybody is concerned about is how to secure these devices and also the privacy of data. And the solutions for privacy of data is also coming from other domains such as software. And I wanted to make a brief mention of the solutions that various people are investigating. So the lay of the land is that how we connect and how we use the devices, that has been changing. So something like 15 or 20 years ago, mostly we had, for these embedded devices, device-to-device communication. In the field of control systems, for example, you had sensors, which were sensing input, and that was leading to control decisions, which was then feeding into the actuarial system that was actually controlling. This is typical in industrial control systems. You'll find examples of that in cars, for example. We have various sort of sensors, such as cruise control, where you sense the speed and then you inject the amount of the fuel that going into the engine to maintain a constant speed. More recently, we have devices to human connection. And when you have devices to human connection, we primarily talk about services. So this could be any of the services that you use in your personal device, for example. And these services, they typically have location/situational awareness. The GPS is a very common thing. Depending on where you are browsing the web from, as you have seen, the search result changes. If I type weather into Google, I'll get weather here for Bochum, and if I do the same thing in Amherst, I get the local weather there. So that provides context awareness, and so this context awareness just feeds into the cloud, which provides these services. With that, we have a lot of issues with securing data. So some of the data that we worry about are in personal IoT, Internet of Things. medical Internet of Things, industrial Internet of Things. So I'll give you one very specific example, maybe wind farm, because I was talking to some people in a wind farm organization just a while ago, only a couple of weeks ago. So this is a wind farm operator, and they own a bunch of wind turbines in California. They own another set of wind turbines in Texas, and they participate in the marketplace. So this wind farm will have to tell the marketplace how much energy they're going to be producing for the consumers. And the national grid company will then make a market between the supplier, this power generation company, and the consumers who will be buying that product. Now, if the wind farm promises that we are going to be delivering certain amount of energy, and if they actually fail to produce that energy, then they'll have to buy that in the market because they have already made a contract with the customer, right? So how do they forecast how much energy they're going to produce? Well, it depends on the velocity of the wind, the direction of the wind, and at any given time, how many of those wind turbines are actually working, because some of them may be under maintenance. So they have sensors, they are connected to the internet, they have weather data. They also have historical data because they have been collecting data over a period of time that, what was the wind velocity yesterday and day before yesterday, and how long did it sustain, and so on. So based on that, they have a model that predicts how much energy they're going to produce and for how long, and how is this pattern going to change, right? So because they own a lot of private data. Do they want this data to go out into the internet, into other people's hand? They don't. So the only information that they want to provide to the grid operator is that this is how much energy I can produce for the next hour, for the next 2 hours, for the next 10 hours, right? But all these other details, are specific to them, which other people should not be, knowing about, and they should be able to secure that information. So in order to do that, they run local computing, and which increasingly is called the fog computing. There are 3 different terminologies that people are using these days. One is called edge cloud. It's computing that happens at the edge. It's also called cloudlet, and it's called fog computing. The word fog computing has been pushed by companies such as Cisco, Intel, Microsoft, etc. So the whole idea is that you have a bunch of edge devices that connect to the fog. They feed a whole lot of data. The fog also derives data from the wide area network, from the internet, and then they process the raw information into something on which you can have actionable intelligence. So one example would be that if you have, say, geolocation services, you don't really care whether the geolocation is coming from your fixed IP address, or it's coming from a GPS device, or it's coming from any number of RF techniques. At the end, it's just a utility that provides what the geolocation is. So what you want to do is you want to hide all of that detailed information and just provide the user with an utility function that says that this is the information, right? So all of that details should be hidden, and this is part of the edge computing. The other thing that we see the emergence of in the IoT space is that people are focused on extremely rapid deployment. So you don't actually wait to prove that a system is secure, that your data is going to be perfectly secure, et cetera, you just go ahead and deploy the system as soon as you think that you have something working. And when a system grows with devices that are both trusted and untrusted, we have to be able to run applications with different degree of privileges, where the trusted and the untrusted components, they coexist. So there is a lot of work which is happening in the software space, and I'll just mention a few of them. There is something called Docker. How many of you have heard this thing called Docker technologies? A lot of you. So of course, Docker, and there is an effort there called the Open Container Interface, which is trying to basically have your software packaged with the libraries so that these libraries are not shared. Typically in an operating system, some of the things that happen is you get signal from other processes you get data from other processes, you can share things with other processes, you can pipe things into other processes. So here with this Docker type of interface, what they're trying to do is make everything stand alone so that an application has minimum information passing between a couple of applications. There's also the Intel SGX enclaves, and a whole bunch of people, even in the embedded space, is also trying to implement something like this. Intel, of course, is in a second generation of SGX, or software guard extension, where basically what they do is when the processor is communicating with the memory interface through a bus, the bus can be observed by other people, the memory can be accessed by other people. So they basically encrypt the memory pages when it goes out of the CPU to the memory, and they're decrypted when it comes back. And the encryption keys are changing constantly because they happen to integrate TRNG, or true random number generator, inside of the processor, which is providing them with a dynamic key. And also in Microsoft, there's an effort called Haven, and this is based on the Intel SGX platform. They're trying to build an operating system which is quote unquote completely secure. So this is pretty much a broad overview, but within the industrial space, there's some consensus which is arising, and if you look at some of the publications and the white papers coming out of big companies such as Cisco, such as Intel, you will see that there is some convergence of views. So one of those views is that the edge devices that we will use primarily in the industrial IoT space and in the medical space, they're going to be inexpensive devices which will have no physical security. And so essentially they are subjected to all kinds of side channel invasive attacks. And they will also have fairly limited computation and security capabilities. So nobody is expecting that these edge devices will be implementing a full-blown AES. I mean, that's the position that these companies are taking. They also assume that these edge devices will then connect with what they call cloudlet or the fog computing. And the primary purpose of fog computing is to provide some degree of autonomy. So in the industrial applications, what will happen is every now and then you lose connection to the internet. And the same thing will happen in medical devices, that every now and then you lose connection to the internet. So whatever environment you're operating in, the devices should continue to operate autonomously, even when there is nothing coming from the external side. So for example, if you're operating a wind farm, and if you just said that I can sell this much energy, and then internet happens to go down, so what happens to the wind farm? I mean, do they continue to operate? What do they do? So they may have energy storage facilities, and when the communication goes blank, they may decide that we'll continue to produce power and we'll divert that power to our energy storage system. Happens in medical applications as well. If you're expecting that somebody from the remote location is going to provide you with input, no input is forthcoming, what happens to your pacemaker? Does it stop or does it continue to operate? So this is the primary function of this computing at the edge, which is autonomy. The other functions that they're going to provide are utilities. I mentioned some of them, such as providing with location, weather, production level, etc. in a factory. It involves repackaging and reformatting the data and hiding the raw information. The third function that fog computing is going to do is aggregation. So which is when you get multiple requests from multiple sites, you don't want to forward those requests to the edge devices, because those edge devices are computationally not resource rich. So you want to group all these queries into a single query, and so that you can serve queries from multiple users with just a single query to the device. It also involves things like caching, maintaining a history of the queries, buffering, and privilege levels. This part will somewhat relate to our talk. At the privilege level, there will be various parties who will be submitting queries to access an edge device. they may or may not have the privilege to access levels of information. And this has to be managed to see who can access the information and who cannot. And some of that relates to privacy and security. There will be secure channels, and finally, there will also be service level objectives. So some of the example of service level objectives is when you're, say, today in the networking world, when you have software defined network, your service level objective might be that I will be able to sustain video at this rate. So that could be a service level objective. So enough of that. I just wanted to give you a very broad picture of where various people are thinking about the security solutions, and particularly in the space of industrial Internet of Things. And there's a whole bunch of software activities that are also taking place. I'm going to be focusing primarily on this in the next part of the talk. So I'm just going to be focusing on the edge devices. So on the edge devices, there are people who envision these edge devices to be extremely tiny dies, which are called dielets. For example, the US Defense Department, the DARPA, has a program which is called the dielet program, where they envision that you'll be putting together a large system, maybe a chip equivalent, by using tiny dies, and all of those dies come from untrusted foundries. And such that when you put the system together, the system should be trusted. So each individual component within the system may be untrusted, but the combination of this thing would be trusted. There's also something called silicon dust, very similar idea that the chips are going to be extremely, extremely tiny, and they will provide with little functions, as opposed to giving you the entire functionality that you normally expect from a chip. And you should be able to pick from the silicon dust and put together a system in which you build your functionality.
Are the dust, are the IP cores or the individual chips?
The individual chips, but they're very, very tiny. So for example, you can think of an example of silicon dust is a tiny chip that just talks to the Ethernet interface, and on the other side, they just put data in a buffer. Okay. So in many applications, when you build a system, you have an Ethernet interface. You have a USB interface, you have a Bluetooth interface. So maybe all of these are tiny dusts of silicon, and eventually they dump data into a buffer. So then you have another piece of dust that can pull data from this buffer and write things into the buffer.
So from a physical point of view, there will be discrete components?
There will be discrete components which not packaged at the discrete level, but they will be packaged at a packaging level together.
Okay.
So you'll pull together these various dies, and then you'll package them together as a chip. So that's
like system on chip kind of
that's like a system on a chip kind of a thing. That's the vision that a lot of people are propagating. And the other thing is they'll be limited in computational capability, yet they should support some identification and authentication functions. So how do you do that when these functions are going to be so limited and they're going to be so tiny that, and you're doing that to build a secure system from untrusted components? So one of the ways of doing that is physically unclonable function, and they can be used to, for example, produce a key that will be used in secure key storage and secure authentication, and also in access control, to decide who gets access to what services from this particular die. So for example, if you have a physically unclonable function, and if you're able to authenticate by using subspace of the entire input space, then you'll be allowed to access certain functions. And if you can authenticate at another different subspace, you'll be given access to another level of functions. So that could be used as an access control. So the PUFs are circuits which create secrets from inherent manufacturing process variations. So when you go through the silicon manufacturing process, there are a lot of things we cannot control, which basically makes these transistors behave slightly differently. And I'll give you an example. We normally, when you go through the manufacturing process, we take a silicon wafer, And we expose that with light to make patterns on the wafer, which eventually form the transistors and the circuits. When you expose that, the patterns that you're drawing today is, say, for the Intel processors, the 14 nanometer transistors. And when you try to pattern at the level of 14 nanometer, imagine that you have a wafer and you have a mask with which you're exposing with light, and you're trying to draw patterns that are 14 nanometers in width. If the light is slightly out of focus, then those patterns are going to change very significantly. And typically this wafer, you cannot control the focal plane of the light any better than, say, plus or minus a couple of nanometers, 3 nanometers. And that's enough to produce tremendous variation in this transistor dimensions, the performance change, and we exploit all of that to basically create keys. There are two types of PUFs that we define. One is strong PUF. In strong PUF, we have an exponential number of challenge response pairs. So we can apply a very large number of inputs, such as a 128-bit input, and we can get a response. In a weak PUF, there are only limited number of challenge response. And the default of the weak PUF is you're not allowed any challenge at all. You just have, so which is basically one challenge, or you apply, you query the PUF, and the PUF just gives you a response, okay? And typically the weak PUFs are being used as keys, and they're being sold by a number of companies, including NXP, Intrinsic IT, Intel, etc., and they provide a secret key. So one example where this weak PUF may be used, for example, in the Intel processors, they have a weak PUF which provides them with a key. And this key is actually never released to the outside world, but this key is used in conjunction with, say, something like an AES function. And if you can use that key to write data into, say, hard drive, which can only be read by this specific processor and by nobody else. The strong PUF examples are arbiter PUF, which I'll detail a little bit, and they typically have 64-bit to 128-bit challenges. And strong PUFs have not gained any traction with the industry. Nobody is actually using strong PUF for any application. And that's because there are a number of challenges associated with the strong PUF. And this is what the rest of the talk is going to be about, that how do you address those challenges. So that's the focus of the rest of the presentation. So let's review what a strong PUF looks like. So the very first strong PUF was proposed by Srini Devadas from MIT. And the circuit structure looks something like this. So you have a bunch of blocks, and those blocks receive a single bit input. So this receives a single bit of challenge called C0. At the input, you create a 0 to 1 transition. And if this input value is 0, the transition happens to propagate along the two red lines. And if this value is 1, the transition propagates along these green lines. And then this process continues until you reach the end. And at the end, because of manufacturing process variation, the delay between this path and that path, they're slightly different. So even though they get the transition exactly at the same time at the input, at the output, these transitions are going to come at very different times. And if this happens to come early, then you call that output 1. If this happens to come early, then you call that output 0, and an arbiter resolves that to a 0 or a 1. So when you apply a challenge, which could be 0, 1, 0, for example, you launch the input transition, and they follow this path, and then they follow a cross path, and eventually when they arrive, they have some variation in the delay. You resolve that to a 0 or a 1. So the whole idea of pushing a strong PUF at that point was that you can apply a bunch of challenges and you get these outputs. And because these chips will have unique features, then you don't need any strong cryptographic function, and you can directly use them for authentication. So that was the original idea. And the usage model is that in the beginning, you will be mining some subspace of, you cannot mine the entire 2 raised to the power 64 or 128 bits of data, but you'll be mining some random subspace of that, and the authenticator will be storing the challenge responses, and during actual use, you'll apply a challenge, obtain the response, you'll validate the product, and you'll delete them from your challenge response database, so they'll never be applied again. So typically think of an ATM card, and if the lifetime of an ATM card is 5 years, and if you happen to use the ATM card at least 3 times a day, every day, then you're going to have how many uses? 3 multiplied by 365 times 5. And each time for authentication, if you use 10 different challenge responses, so that's how many you need to store, and you'll never be reusing them, so that nobody can actually mount spoofing attack or cloning attack. Some of the properties that we need out of the strong PUF is that in a manufacturing scenario, when you produce different PUFs, they must be highly unique, so that 2 PUFs are never identical. The other property that we need is that the outputs are highly unpredictable, so that nobody can actually build a software model of how this PUF is going to behave, because then we have cloned the PUF. And the third one is that it must be highly reliable, which basically means that if I query the PUF with an input challenge with supply voltage and various temperatures, the answer should be the same, and the answer should not change. Okay? It turns out that all these 3 are problems. So first, we cannot guarantee that a PUF is unique, even though we assume that a PUF is unique. We cannot guarantee that we cannot build a software model for it, and we cannot make this thing very reliable. So we have addressed actually, to some extent, all of these problems. And today I'm just going to be talking about 2 of them. I'm going to skip the third one because that involves low-level transistor-level design, which I don't want to get into today. So the problem with the uniqueness, if a manufacturer produces millions of PUFs, how can you ensure that no 2 PUFs are alike? Okay? And that fundamentally gets us to another question, that what does it mean to 2 PUFs to be even alike? So suppose I give 100 challenges to 2 PUFs, and they produce responses such that 98 of those responses are identical, and 2 of those responses are different. Are these 2 PUFs different, or are they alike? Right? From a practical point of view, these 2 PUFs are not different, because in a standard authentication scenario, you're not going to apply maybe that many challenges, and you're going to apply a few challenges, and if you get the same answer, those 2 PUFs are indistinguishable. So we have to somehow define the alikeness of PUFs. Similarly, the definition of security is if an attacker can predict response to a challenge, the attacker has effectively destroyed the security. So how can an attacker predict a response? Of course, it goes into model building. But then we have to answer a question, at what prediction rate do you declare the security has been breached? Because how accurate does my modeling need to be? Does it need to be 99% accurate, or do we say that at 90% the security has been breached? So what is the level? And there is no accepted definition here. I'm just throwing the questions because nobody has really answered those questions. Lastly, reliability. How do you guarantee that PUF response does not change with voltage, temperature, and time? And so that leads to circuit design challenges, which I'm going to skip today. So let me talk a little bit about improving uniqueness of PUFs. So the basic question is, can uniqueness be guaranteed by design alone? So what has been originally proposed by people who pushed this idea of strong PUFs, primarily from MIT, is that if you produce them, then they will just be unique, and we can directly start using them for authentication. Turns out that they need not be unique, because the variance of the PUF response depends on the manufacturing process variation, and some of the manufacturing process variation is very systematic. It is not purely random. So for example, I mentioned that when you're going through the fabrication process, a wafer may be out of focus. It's very systematic across all chips on the wafer. They're all going to be out of focus. So how can you guarantee that manufacturing process variations will be unique for each puff. So to do that, we have to test. We have to go through a testing process to make sure that in a factory, all the puffs that we are producing are unique. And I must mention here that even though people keep talking about these puffs having random process variations, that the definition of the random typically is a very poor one. Anything that we don't model, we tend to describe as random. But it really need not be random. It can be very systematic. It's just that we don't model that behavior. So what we want to do is we want to test for uniqueness. So let's look at a problem, a potential solution. For all puffs, we apply a set of challenges and we collect their responses and perform a comparison to decide which ones should be eliminated, which ones we should not sell because they produced the same response, right? So if two puffs produce the same response, we should sell only one of them and just discard the other one. And if you do this offline, then we'll have to, what in the manufacturing test world is known as we have to re-socket those chips. So first time you socket the chips to collect data, then you perform analysis, then you again socket those chips to see which ones should be eliminated by applying the challenge. And that is completely impractical because multiple socketing in a factory setting is very expensive. Just to give you an idea, I will just pick one example, say Intel processors. And according to EE Times, Intel produces about 100 million processor chips a quarter. Okay. So if you're testing each processor for about 5 seconds, okay, just picking a number, then you will need 500 million seconds of test time per quarter, right? And so you can do a simple math and calculate how many testers would be needed to give you 500 million seconds in 3 months. Okay, obviously you cannot get from one tester. You're going to need multiple testers. As you buy these testers, those testers would have to be housed in buildings, and assume that those testers occupy some amount of area. You can compute how many million square foot of manufacturing space you're going to need. And now if you say that these chips must be tested twice, you can see that the whole entire logistics of manufacturing just breaks down. So that is not a very practical solution. On the other hand, if you just plug in the chip on a tester and we collected data and we want to do online checking against a database of all the chips that we have produced in the past to see if this is similar in response to something that we have produced in the past. Then what you have to do is, if you have produced 100 million chips, then you have to run linear comparison with 100 million chips and then decide whether this should be discarded or it should be sold. And that again is a completely impractical proposition because you can't plug in this device and then run 100 million comparisons on the server. So that is not going to work. So the big question is, how do we make a pass-fail decision in single socketing without putting the chip twice on a tester in a high volume manufacturing environment? And we should make the decision to accept or reject the part in fraction of a second. And of course, we cannot do that if we compare the response of this part with all the other parts that we have produced in the past, right? Because that will completely break down. So how do we solve that problem? So assume that we are applying some number of challenges. And so a chip I produces the response Ri, and we have passed n number of chips previously. And so we have to run a comparison of responses of all the chips that we passed and sold previously, and the chip that we just produced, its response should not match with any of those chips that we have sold in the past. So we don't want to make, we want a solution which can be really, really fast. Okay. Now, I make a digression and try to go back and answer a question that we asked previously, that how do you define uniqueness anyway? Suppose we apply 1 million challenges and 2 puffs differ in response in just one challenge. Are they different? And of course, they are not different for practical purposes. So somewhat arbitrarily, we say that two PUFs are identical if they differ in response for less than 10% of the challenges. So we had to adopt that definition, because without a definition, we cannot make a go, no-go decision or a pass-fail decision at the tester. So this is something that we define. Of course, this can be changed. So we say that two PUFs are identical if they're given the same set of challenge, if 90% of the answers are the same. Okay, then we say that those two PUFs are identical. Even with that definition, if you want to distinguish between those two chips, remember that 90% of the answers are same. And so if you want during authentication that we misauthenticate 1 in a million times, then we have to apply 131 challenges, assuming that they're uniformly distributed. If you want misauthentication 1 in a billion, then it becomes 197 challenges must be applied in order to do that. So even the 10% definition to us doesn't look adequate, but let's just go with 10% definition, because if you require two PUFs to be more than 10% different, after manufacturing we'll throw away a lot of PUFs because they simply don't meet that, and that will increase the cost of PUFs. So I don't want to elaborate on this problem a little bit more because of the sake of time. I'll skip this slide and directly go into solution. So for solution, what you propose is we will use multi-index hashing. And multi-index hashing quickly searches nearest neighbors in the Hamming space. This technology was developed primarily for the search engines. So for example, when you run a Google search, they have to be able to sort the pages that are extremely similar in information and group them together. So, so when they group these pages together, they use this principle of multi-index hashing. So how does multi-index hashing work? So let's simplify this problem further. Suppose we have applied 100 challenges and we got 100 responses. So we got these 100 responses. We can think of, we apply the same 100 challenges to all the PUFs, okay? And from each PUF, we get a different response, and we can represent that with this string, that 100 bits of response. We split this into 5 buckets, and each bucket is 20 bits. Now we want to search that these 20 bits, have you seen them in the past? And so we want to do a similar search for these 20 bits and a similar search for these 20 bits. So we parallelize the search operation, and we are doing it 20 bits at a time. Now remember our definition that if 2 of those bits are mutated, okay, and if I find that in the database, then we say they're identical, because our definition was 10% of the bits, if they're different, and yet we find a match, then we say that they're identical. So in this problem, it turns out that we will need to search. We take this 20-bit string, and 2 at a time, if we mutate, we get 20 choose 2 combinations. And because there are 5 buckets, we'll have to do 950 lookups and find out whether that exists in the database or not. And if you find out that that exists in the database, then we will run a linear search through this PUF, through the 2 PUFs, to make sure that they are not identical. So it looks something like this, that here is a chip under test. We apply 1,000 challenges to the chip under test, and we collect 1,000-bit responses. From those 1,000 bits, we randomly choose 100 bits, but those are the fixed 100 bits that we're going to compare. And we do this multi-index hashing, and we shortlist a set of candidates on which we'll perform full response check, and then at the end we'll make a decision. If they're sufficiently different, we will say that this chip's responses are sufficiently different, and therefore they have passed the test. Otherwise, the chips have been rejected. So this is kind of the procedure, and performed experiments on this procedure. We assume that the tester is running at 100 megahertz speed, and And we also implemented the circuit to perform this test automatically. DFT stands for Design for Testability. So we built circuits on the chip itself so that it can collect those 1000-bit responses. And the bottom line is that we can search in 0.55 seconds against the database. And in C++ implementation, we can search in 0.15 seconds this entire database. And we can test this chip in less than a second to make a decision whether we have seen this response in the past or we have not seen this response in the past. Okay, so this is something that you need to do during the testing phase in order to make a decision. And here's some results.
Were the 100,000 chips actually built?
No, it was in simulation.
Oh, okay.
It was in simulation, yeah.
What was your machine, target machine of this 0.55 seconds?
This 0.15 seconds? It was a standard, Intel desktop processor that we had. Yeah, just
big server farm.
no big server farm. Just a desktop machine. So the basic principle here is we had to be able to search through the database very, very quickly. And we applied some of the same search techniques that, say, for example, the search engines use to search through the database and make a decision, go, no-go decision, whether we have seen this in the past or not. Next, I'm going to be talking about improving security of the PUFs. Okay. So we have already seen this arbiter PUF. And after the arbiter PUF was designed, it was observed that if this transition happens to traverse over this path, then I can simply write an equation that the delay of this path is this delay plus that delay plus that delay. And because of the number of edges possible in the circuit, in each block you have 1, 2, 3, 4 edges. And if there are, say, 64 blocks in this, then we have only 4 times 64 pieces of information. So the idea is when you apply challenge and you obtain the response, if you can write equations for those, we need to just solve for those equations. And 4 times 64 is 256. So if you apply 256 challenges, then you'll be able to solve those equations, and we have broken this path. So that was, which was shown previously in 2004. So at that point, they said, okay, the problem is that we are performing linear addition. And therefore, we need some kind of nonlinear composition of this information so that we cannot write a simple equation that delay equal to a plus b plus c, but it is some more complex function. So at UMass, we actually designed 2 of those circuits, one of which was fabricated and the other one was not. And the one which was fabricated is based on current, and the one which was not fabricated was based on voltage. So this is how it works. So suppose we design a circuit that looks like this. So these are the various transistors, and we apply an input and we look at the output. If we plot the input-output behavior in terms of the voltage, if we apply this as the input voltage, that is going to be the output voltage. And because these transistors will have manufacturing process variations, in each block, they will produce a different transfer characteristics. And as you can see, that this transfer characteristics is highly nonlinear. So if you apply an input voltage here, and then if we measure what the output voltage here is going to be, it's going to be one of those values, and then that gets transformed further, and eventually we have 2 different voltages, and we sense which one is a bigger voltage than the other one to make a 1-0 decision. And this is known as the nonlinear voltage transfer characteristics. It is different from the delay characteristics, and this was designed by one of my students. And by using machine learning, he showed that even if you apply 100,000 challenge response, you have a prediction accuracy of about 80%. And remember that your prediction accuracy baseline is starting at 50%, because for a PUF, if you're just randomly guessing whether it's 0 or 1, you'll be correct 50% of the time. So you're starting with a baseline of 50%, and you can go up to about 80%. This compares to, say, for arbiter PUF, Uli here, he showed that with just 600 challenge response, you get a 99.9% prediction accuracy. So this shows that this is a better circuit. But we are still not happy because it was only broken by using one machine learning algorithm. So by using support vector machine. So there have been many different types of PUFs, strong PUFs that people have designed. And there have been, so this was, for example, attacked using logistic regression. This was attacked using evolutionary strategies. And this one was resistant against support vector machine only. We still don't know if we change the machine learning algorithm, whether somebody will be more successful or not. So that is a problem. So then we ask a couple of different questions. One question we ask that suppose we design a PUF and we try to attack this PUF using machine learning, okay, by model building activity. If we succeed, what can you learn from it? And if we fail, what can you say about the future, whether it can be broken or not? So those are the two questions. So first, what can you learn from it? Because if you can learn something from it, then we can actually improve this design to make it more machine learning resistant. So in order to do that, what we did is we actually, instead of looking at a very specific circuit, we looked at a very abstract model for the PUF, okay? And we performed a bunch of studies on the abstract model. And as far as machine learning is concerned, we worked with a number of techniques which collectively are known as meta-ensemble techniques. And I will be talking a little bit about that in a few slides. So let's look at what is the abstract model idea. Now, in my group, we had developed this voltage transfer characteristics PUF. At UMass, another professor, Burleson, he developed this current-based PUF. The current-based PUF. And at MIT, they developed this arbiter-based PUF. All of them, they look very similar in structure. In one case, we propagate the voltage from input to the output and measure the difference. In one case, we propagate the current from input to the output and we measure the difference. In the other case, we propagate delay from input to the output and we measure the difference in the delay, right? So in general, this is just, we can think of this as some arbitrary function. We are propagating this in some input value. We are going through a function and we are propagating these differences. And at the end, we just have a comparison. So how can we model this function? And it really doesn't matter whether it's a delay or voltage or current. We approximate this function with a table. So basically what we are doing is any function, if it's an analog function, can be discretized and can be viewed as a table where you apply an input and you obtain an output. And it really doesn't matter how it has been implemented at the circuit level. Whether it's a delay or current or voltage, we abstract that as a function. The function is discretized, you apply an input, you look at an output, and at the end the function can be described as a table. Okay? So it turns out from a machine learning point of view, we already know that at the end, if these two function distributions are uniform, then this is the hardest problem for machine learning to break. If they have a bias, then machine learning algorithm, they tune on the bias and they build a model and they can break this algorithm. So we then figure out that what we need to do is build these tables so that these output probabilities are somewhat uniformly distributed, but they're random. Because uniform distribution here is the worst case for machine learning algorithm. Okay? And once you know that, we can go back and build circuit at the transistor level to satisfy those properties. So we build these tables. So now the question is, how many entries should these tables have? So in this particular case, we show a table with entries, 4 entries, and we could have more number of entries. So these tables represent abstraction of the circuit transfer function and represent it as a discrete function. Okay. I will skip through some of those slides and simply go into results and show that when we performed experiments with these, we found that if you make the table size equal to 4 and as we apply the challenge responses, then this is what happens with our model building accuracy. Our model building accuracy keeps improving, and the machine learning technique which is most successful is the gradient boosting technique that pretty much gets us to close to 100% accuracy. And some of these other techniques, like Uli worked on support vector machine, that gets you around here 80% accuracy, and logistic regression gets you around here with these kinds of accuracy. But on the other hand, if we change the table size to 128 entries, then we find that we pretty much cannot break this PUF at all, because with the bagging technique we are still around 50%, and with gradient boosting technique, which is very, very expensive, we still don't break the barrier. So from here we conclude that when you're building the strong PUF, it's not the cascading of the structure which is a problem. It's just that each individual block needs to have enough entropy, enough variation, so that we can have so many discrete points.
Can you go back one slide? What exactly is the table size?
Table size is you have an input to the output, and table size describes when you have an analog function that if this is the input, that is the output. You can model the analog function as any analog transfer function. You can model it as piecewise linear function, right? And the number of discrete pieces that you have is the table size. Is that clear?
Quantize it?
What?
We somehow quantize this.
We just quantize this. So the number of discrete segments that you have, so it basically says that the number of discrete segments that we need to have should be very, very large. Otherwise, we'll be able to break it with machine learning.
So in this example, table size is 4.
4.
Right? Yeah. And then you have a...
So we experimented with table size 4, and we can see that we can pretty much break that with machine learning attack. But if the table size is 128, we almost cannot break it.
If you go back, does it, I mean, you have to the left are the inputs, right? Like
Yeah,
like
this is
size
input and this is
4,
output.
right?
Yeah.
And then does it depend how the outputs are assigned? I mean, whether this is nonlinear or?
This is nonlinear, the outputs, but at the end we just compare the two outputs and we just do 0, 1.
I mean, it resembles somewhat an S box, right?
Yeah.
2 input in.
Absolutely, it resembles an S box, and if it's a small, then we can break it with machine learning attack.
Did you look whether that depends on the quality, like the statistical properties of
Yeah.
the tables, right?
Yeah. So I'll have a slide on that.
Okay.
Yeah. So the bottom line is we need a large table, which basically means the building blocks that we have should need to have. There should be, if it's a monotonic function, a lot of times you can just model it with only few segments. So it should be a non-monotonic function with a lot of changes, so that we need this large number of entries.
But I understand here, if we have a better accuracy in quantization, it works worse, right? I mean, because the accuracy of the model is lower when we have a higher accuracy in the quantization.
When we need higher levels of quantization, then we cannot build a machine learning model.
Okay. But this is just the model accuracy, it's not about the attack bit, right?
Because the attack becomes harder if you
Attack becomes harder as we have
quantization.
more quantization.
Okay.
Yeah, and the question is not more quantization or less quantization. The question is, to model the input-output behavior, do we need more quantization? So that is the key question. So it should be such that we need more quantization, which means the circuit behavior is changing rapidly so that we need more quantization. If it was just growing monotonically, we don't need quantization, right? So the behavior that we come up from the circuit is that not only it should be nonlinear, but it should be changing as we change the input, and changing rather rapidly. Then it will be difficult to break.
Do we have any symmetric people here in your legal school? Yeah.
So the second thing we find is that, so first observation is increasing the size of the table increases the machine learning resistance. The second observation we find that given sufficient entropy, machine learning resistance is possible. So it is not a problem with the structure of the PUF, but it's the lack of entropy which makes it breakable with machine learning. We also observed that among all the machine learning techniques that people have used, the meta-ensemble algorithms are the most potent, and specifically the boosting and the bagging perform far better than all previous machine learning algorithms that were tried. So basically what I did is, of all the machine learning algorithms that are used today, we unleashed all of them to figure out which one is most effective, and then we found that these two are the most effective. Now coming back to your question, impact of bias in the function, right? So what if so remember in the table we assume that the output values are uniformly distributed. What if it was not uniformly distributed? What if the output value was Gaussian? That is very likely to be this value and then also spreads out at these discrete points. We find that if it is not uniform, if it's Gaussian, we have a better modeling, we have better luck in attacking that entity. So this actually also confirms what is already known to the machine learning community, that if input variables are uniformly distributed, that is the hardest case to break in terms of machine learning. And as you add bias, then it becomes simpler and simpler to break it using machine learning. And in this case, even Gaussian, many people would not consider to be biased, but when you switch to Gaussian, it becomes relatively easier to break. Then we looked at another thing that here, Georg Becker, he looked at breaking PUFs that uses digital nonlinearity such as exclusive OR gates. And we found that if you use exclusive OR gates and we have 3 different PUFs, versus if we just take this table size and if we make it bigger, then it turns out that this is better than doing that. So in other words, we showed that digital nonlinearity is not really helping with machine learning resistance. What really helps with machine learning resistance is intrinsic entropy of the building block. So post-processing it with digital nonlinearity is not helping it. But just the basic source of entropy helps it better.
So if you have this, you have like a lookup table
Yeah.
of 8, right? This is really a model of the analog transfer function.
That's right.
Is that right?
That's right.
So you look at like 8 input values, and the output is also one.
That's right.
One
That
out of 8.
one of those values. Yeah.
Can you can I ask another question? Can you build the whole thing without going analogs? Then, like in this example,
If you build pure digital addition, subtraction kind of a thing, then it's very easy to break using machine learning.
no, but let's say that's why I just asked whether we have symmetric people here, this 2 to the 3, could we just use that as a 3 input, 3 output lookup table?
You could do that.
Yeah, but then you would have not 1 line, but like 3 bits going out.
That's right. Yeah, that's right. You have 3 bits coming in. Yeah.
And max these 3 bits.
There's max those 3 bits. Yeah.
But then you wouldn't have any reliability problems, right?
You would not have any reliability problem. The circuit size will be big.
Right.
Yeah. So this would be a perfect
And
solution.
it's not perfect.
The circuit size will become bigger, and that's what we are trying to address. And that's a very good question, because that leads into my next slide as how to reduce the circuit size. So I'll skip through that, and this is my next question: how to reduce the circuit size. And if you are if you happen to just put those digital boxes instead of analog functions, and if you want to have as few tables as possible to build this PUF, then how will you do it? So it turns out that we built these tables to be relatively small. Now remember, previously we shown that if these tables are large, then it's very difficult to break in machine learning. If it is small, very easy to break. But what we are doing is we are using small tables here, and in some ways, the small table is almost like confusion stage, because when you add a table, you are confusing, and small table means it's a small confusion. And this, in some ways, is like a diffusion stage, where we have a log structure of similar tables, and then eventually you produce this output. So let's look at it. We have two tables coming into this mux, and they produce inputs S1 and S2, and here we produce S3 and S4. We take S1 and S3, and then we take S2 and S4, we resolve it, and then we use that as a select input, and then we produce these two outputs, and you continue down this path that way. And so by doing that, we have basically made this structure more complex. It was not just a linear cascade, but it's more like a log structure. And what we found is that even when we input the structure into the machine learning algorithm, so machine learning knows the structure of this, and it had a hard time breaking it. So even with small size tables, okay, and even with the known structure, all the machine learning algorithms that are much harder time breaking this. Further, what we found is that these cells, if you make those tables identical, they're not different, they're identical. Machine learning still had incredible problems breaking the structure. So based on that, we came up with something which is much simpler in structure. And as I'll show you, that we went down to table size of 16 entries, okay, from 128 to 16 entries, and we found that the prediction rate was same 61% as with 128 entries in the table. But instead of using a linear structure, we used a log structure for it. So the total entropy budget, it reduced to 576 bits of information. So in some ways, if we are just implementing this not as analog function, but with just pure table lookup, with if you just have 576 bits of information, then we can build a PUF which is very, very hard to break for a machine learning algorithm. And so this shows that large area savings is possible, but our goal is still not to use table lookups, but to use analog blocks and to transfer this into analog design, such that we will have a design which is extremely hard to break using machine learning algorithm, but still very, very small. And that's the last part of the presentation which I did not present, how to make this more reliable and how to make this analog and more robust, because that gets down to transistors, and I skipped that part. So we proposed a new PUF structure, and that gives far better improvement in machine learning resistance compared to anything that's known. And we did that by performing studies to understand techniques to increase machine learning resistance. We also identified that bagging and boosting techniques in machine learning, they work the best in terms of attacking. And then we presented structures to save area. So that kind of brings me to the end of the presentation.